Hello students, welcome back. Let us resume our discussion in section 4. Hopefully we can conclude it. Previously we went through the multiplicative property of Euler torsion function. We went through two different types of proof method, but let's not worry about any of those proofs. This time let us talk about how to utilize it. Here's the first application. Let p be a prime number and k be a positive integer. Then phi of p to the k power is expressed like this. And then here, if you use the multiplicative property to this prime factorization, you're going to get this general formula. Let's prove the first identity here. Out of all positive integers not exceeding p to the k power, in other words, 1, 2, 3, 4 up to the p to the k minus power, excuse me, not p to the k minus 1 power, p to the k power. So there are total p to the k power elements in this set. Now among this p to the k power, these numbers, p to the k minus 1 power numbers, are not relative prime to p to the k power. These p, 2p, 3p, 4p, and so on, up to p to the k power, or p to the k minus 1 power times p. So how many are there? P to the k minus 1 power. All the other numbers have modular sum r, where r is greater than 0 and less than p. So they're all relatively prime to p, and consequently relative prime to p to the k power. These, of course, are not relative prime to p to the k power. And how many are there? Count. First power? No, 1p, 2p, 3p, p to the k minus 1 power times p, yeah? So, subtracting one from the other, I can see the number of elements that are not relatively prime to, that are relatively prime to p to the k power. Here is a list of integers among these. So, the subset here that are relatively prime to p to the k power, that are not relatively prime to p to the k power. So if you want the number of elements that are relatively prime to p to the k power, subtract one from the other, we have that. Sorry, they're confusing, relative prime, not relative prime, and not. I said it backwards several times, so do not completely trust what you hear, trust what you read. So in other words, we got this by just simple counting and brute force computation. Now let us apply the multiplicative property to this based upon the prime factorization. Then you're going to get this formula. So n can be written as this multiplication, and then each distinct prime factor, or any powers of those distinct prime factors, are relative prime, so we can apply the multiplicative property and decompose them out. So we have this final product of phi of p to the n power for each index, and apply this to each pi, we are going to get pi to the ni power minus pi to the ni minus 1 power. So that's going to give me the first equality. How about the second equality? From here, just factor p to the n power out for each index. Then what's you're going to get? 1 minus 1 over p for each index. And get all those 1 minus 1 over p, that multiplication separately. And p1 to the n1 power, p to the n2 power, all those out. And they multiply into n because they all came from the prime factorization of n to begin with. So that proves the second equality. And then they're going to give me practical computation method for phi of some relatively large number, provided that I can do the prime factorization relatively easily. Here's an example. Calculate 360. Phi of 360. Not too bad. 360 can be decomposed as prime factors like this. And then 2 to the third power, alright, third power minus second power. 3 to the second power, second minus first power. And then first power minus 0 power for prime factors 2, 3, and 5 respectively. We get, well, let's see, 8 minus 4 is 4, 9 minus 3 is 6, 5 minus 1 is 4. Yeah, multiplying those, we're going to get 96. This kind of computation is something you can handle with just easy paper and pencil computation as well. And here is Euler Phi Computation using Wolfram Mathematica. Even if you have something more complicated here, not too bad. This thing times 10, so all you get is fourth power and second power here. So this is fourth power minus third power, and 3 that stays the same, and the second power minus first power. So fourth power minus third power, 16 minus 8, so that's 8. Third power, so that's 9 minus 3, that's 6, no change there. And second power, 25 minus 5, so I'm going to get 20. So 8 times 6 is 72 times 2, so 144, 0. So is that it? Oh no. 8 times 6 is 72. 72 times 2. Something is not right. I didn't do it right. Fourth power, third power. 16 minus 8 is 8. That's right. 9 minus 3 is 6. That's right. 25 minus 5 is 20. That's right as well. So 8 times 6 is 48. What was I thinking? 8 times 9 is 72. Sorry about that. 48 times 2 is 96. So 960. Yeah, okay, that's what happens when you speak and do mental math at the same time. So even for a little bit larger number, the computation can be done kind of like this. And then if you use handheld calculator, then you can do even better. Okay, all right, that was easy. Okay, sorry about a bit of a mental math computation mistake, but please forgive me about that. Next, if n is greater than 2, prove that phi of n is even. Okay, all right. Phi of 2 is not even. Phi of 2 is 1. So phi of 1 is also 1. And then anything beyond, we have to have an even number. Let's prove that. Why? Well, in order to use this, we'll have to take a prime factorization. And then, let's see. If you have any odd prime, primes like this, then this prime is 3 or 5 or 7 or 11 and so on and so forth. So that's an even number. They're all odd number, excuse me. They're all odd. So p minus 1 is even. So here you're going to get so p to the certain k power minus p to the certain k minus 1 power times some others. And there may be many others, but it doesn't really matter. We can do it like this: p to the k minus 1 power out, p minus 1, and then others. And then that's even. Why? Because this is even. So if you have any prime factor greater than 2, 3, 5, 7, and so on, any odd prime, then p minus 1 is even, so no problem. And what if there's no odd prime factor? In that case, we have to consider n is 2 to the k power only. And then in this case, k is greater than or equal to 2. You cannot have k as 1 because in that case we are going to get phi is 2, but n is greater than 2. Or maybe I can write like this. In that case, well, we can consider that separately. And that's what I did here. So you can express it as divisible by 4 or divisible by some odd prime. So for any odd prime, we already went through that. Factor k minus 1 out, p minus 1, and that's even. And when divisible by 4, then you can do the same. Let's keep it open. You can do the same thing to factor of 2, and we cannot use this one here. 2 minus 1 is just 1, but this one here, that's even because k is greater than 1. So if k is 1, then we have 2 to the 1 minus 1 power, so this thing will not work. But then again, n is greater than 2. So either way, it's an even number. Okay, it was a bit harder, but either way, we went through an example of this. Do you have time for this 4.8? I don't. Let's stop here and we'll do 4.8 in a separate video. Sorry, I could not complete it. I'm gonna need another video for the completion.